Yours.
Thank you very much, Federico and Gabriele, for inviting me, and everyone for being here. So today we'll talk about diversity when we divide a community in subgroups and how the diversity deteriorates when you do this division. This is joint work with Victor Verdugo at Universidad O'Higgins and Sebastián Pérez Salazar from Georgia Tech, but joining Rice University in next fall. Okay, so stop me anytime if you have any questions. So we know that diversity is a very complex concept and also multidimensional, and usually is used to characterize how heterogeneous is a community or how complex is a community. But there has been application after application that has shown that diversity is kind of like a desirable property in many decision-making tasks. For example, it has been shown that diverse teams make much better decisions than individuals or all male groups. And also when model training for machine learning, there has been some experiments that show some bias in the data set because in speech recognition, for example, there is a much higher rate of misidentification for Black people more than for white users. And the same you can find in facial recognition, okay? So as I mentioned, diversity kind of bring benefits to multiple decision-making tasks. As I mentioned in the data training, also like having a diverse data set can improve this, but also in hiring because kind of improve the social mobility, or crowdsourcing because you will have a multiple viewpoints on some specific topic, or matchmaking because it may increase engagement for the platform, or also recommendation because you kind of avoid this bubble effect that some of the social media has. And in the two other that I already mentioned. Okay, so just to narrow down the discussion for today, I want to talk about what is representation in team formation. Just give an example for this. Chile is currently writing drafting a new constitution after a political crisis in October 2018. There was a referendum later where the majority of people, around 80% of the people, voted in favor of drafting a new constitution. And after months later, there was an assembly that was elected and is currently composed by 154 individuals. But the thing is that this assembly, well, it's about to finish in a couple of months. It should be ready, the draft. But usually in the process, the assembly divides into committees and subcommittees to discuss certain topics such as the political organization, political system, or some societal rights, etc. And then after that, they propose a draft for the assembly, and the assembly votes this draft either in favor or rejection, and then it comes back to the committee and so on. Okay, so there were many specific requirements for the assembly and for the committees as well. For example, gender parity, or the inclusion of indigenous people, also independent organizations, and of course, the classical political parties. Okay? So one natural question that comes there is, how do we split the members in the subgroups such that we can represent as much as possible the multiple viewpoints, political viewpoints from the assembly, right? And this kind of like is a natural question, and is the diversity is, the benefits of diversity is kind of obvious because we don't want a specific group to kind of push for their own political agenda in the assembly, right? Okay, so, but there is another key question here after this one is, how do we measure this representation and how do we measure diversity, right? It's kind of a key question. And the thing is that the metric, of course, highly depends on the decision maker and the objective and the aspect that this decision maker may have. But there has been a lot of study with respect to diversity, especially in ecology and biology. And we can go back even to the 1949, where Simpson proposed a way in kind of we can measure diversity given a distribution of types from the community. Okay, so this kind of new metrics are called sample-driven based on abundance, meaning that you have a distribution over types, and then you output some metric with respect to this distribution. Okay, so what kind of one specific metric in this case would be to count, for example, the number of types you have in it. Okay, of course, this is not good because only measure the richness of the community. Okay, so for example, if you have 4 types, then it will tell you, oh, four is the number of diversity. But also you would like, for example, to measure kind of what is evenness, which is like what is the imbalance that is between different types. So this is what distribution brings to the sample-driven base metrics. But in this sector, only you are measuring richness and evenness. Okay, but you're not considering, for example, here what is disparity, what is the difference between two types. And that's when the community developed the similarity-based metrics. That somehow you measure how similar are the types. Okay, so most of the diversity based on these two things has been studied in ecology, but many other disciplines have considered other measures, kind of like geometric or distance-based. For example, in recommendation, there is some way to measure diversity in terms of volume of a specific object, and etc. So. And recently, the AI and ML community have considered metrics that kind of incorporate inclusion concept into the metric. Okay, so beyond that, I mean, you may find other ways to measure fairness or diversity in this case, which is data summarization, fair clustering in economics, etc. You may find other ways to measure what means diversity. Okay, so for today, we're going to focus on this sector because this area, because it's it brings many ways to kind of express this thing as a mathematical object. So as I mentioned, the Simpson proposes in 1949 kind of the first way to measure diversity, and is based on this distribution over types. Okay, so let's just formalize that. So let's say that we have R types. Okay, and we have a distribution over them. So P1, for example, denotes the proportion of individuals of type 1 in the community. And of course, these values P, they sum up to 1. Okay. Okay, so Simpson considered the following: consider the probability of selecting two entities of the same type in two random draws with replacement. Okay. So this specifically corresponds to the sum of the squares of the p's. Okay. So the thing is that there has been many other metrics that consider this as an input, just simply the distribution over the types. And in ecologies, there was some kind of concern in how to compare two different metrics. For example, there is another metric that you might consider is the entropy of this distribution. And the main concern was how we compare these two, because they move around different units. Okay, so for that, the community decided to take, for example, the inverse, a multiplicative inverse of the metrics. And in this case, we can define the Simpson diversity metric as 1 over the sum of the squares. Okay. Okay, so this number specifically has several desirable mathematical properties. For example, it's continuous function over the distribution P, and it's also symmetric, meaning that if you permute the values of P, then you get the same index. Okay, and finally, evenness, which means that this value here, this ratio, is maximized when you have the uniform distribution. Okay. So one key idea in the Simpson diversity metric is that kind of weights more on common species, common types, more than in rare ones. Okay, we're going to see that with some examples. Okay, so as I said, this metric moves around two values, 1 and R, and reaches the maximum value when you have the uniform distribution, okay, which is R, and reaches the minimum value when you put all the weight in one type. Okay, so it means that there is effectively one type in the community. Okay, so just to give you an idea what this number means is, let's consider that we have 7 types, okay? And we have the distribution corresponding in different subgroups. So for example, I'm putting 6 subgroups, okay? And the effective number is just another name for diversity metric. So for example, in subgroup S1, we have a uniform distribution. So we have effectively 4 types, okay? But S2 is a richer subset because it has 5 types. Okay, but it's still the same as even. Okay, we have the same distribution, the same proportion in each type. S3 instead is same richer as S2, but it's less even because the last type has less proportion. Okay, so it says that effectively you have 4.45 types in this community. And S4, it's much worse than S3, so it's almost approaching to the value of 4, right? Because the value P for type 4 is very small. And S5 is less even, okay? You're putting more weight on the first type. Okay? There is more weight on that because it is at 0.5. And that's what I'm saying is that this metric kind of weights more on common types, right? That's why if we put weight 0.5, then we still have 3.42, which is not much less than 4.08. Okay. And finally, you can see this effect on the last group, S6, in which we have 3.53, but it's much richer, but it's still kind of imbalanced to the first type. Okay. Okay. So I hope that there is some kind of clear idea of what this metric is. So I mentioned to you this question of splitting a group into subgroups. And also we have our metric, which is a Simpson metric. So in this work, we introduced the first model that studied the deterioration of the diversity when you divide a group by using this Simpson metric. Okay. So the first question that we address here is that when can we guarantee, in which kind of instances we can guarantee that the diversity of each subgroup is as diverse as the whole community? Somehow we can preserve the diversity of the whole community in the subgroups. Okay. I'm going to formalize that in a bit. And then if this is usually not necessarily possible, so when the answer here is negative, then the natural question is, okay, so when can we find, how can we find the best division that kind of guarantees that the least diverse group is as diverse as possible? Okay, so you're maximizing the minimum diversity among all the groups. Okay. Also, our work, if you're interested, we consider other insights in the sense that we kind of talk about more applications and also general models for this problem. Okay, so let's formalize the model. So the input for our problem is a population of R types, okay? And I have an R-dimensional vector of integers, okay? So I'm gonna have B1 to BR. And this B indicates that the number of individuals of the type I, okay? So for example, B1 says that I have B1 individuals of type 1, okay, and so on. Okay. So with that, we can measure diversity with respect to the Simpson metric. And it would be the following. So for example, if the proportion would be of PI, of the type I would be PI equals to BI divided by the sum of the B. Okay. That's the proportion of type I, which is exactly BI over the norm 1 of B. Right? It's pretty simple. There's not nothing crazy. Okay, so with that, I can measure the Simpson metric. So the Simpson metric will tell you that the diversity of B is 1 over the sum of the squares, which then end up being the square of the ratio between the norm 1 and the norm 2 of B. Okay. So we can generalize, I mean, we can define now what is diversity metric for a specific R-dimensional vector of integers that goes to a value between 1 and R. And it's going to be the square of the ratio between the norm 1 and the norm 2 of the vectors. Okay. So it's as simple as that. So with that, so now the input is, as I said, is this vector of numbers. It would be the following. So the problem is, given a k, given an integer k, we want to split the population in k subgroups, meaning k vectors of integers, okay, of R-dimensional integers, such that it's effectively a partition, meaning that is B equals the sum of the vectors. Okay, and also that the minimum of the diversity of the subgroups is maximized. A little bit think about this. Any questions on this formulation? Okay, so when you're considering a partition for the community B, then there is always at least one group that kind of suffer more than the rest. Okay, that for sure you're going to lose. That you have the following is that the minimum of the diversity is always there is one subgroup that gives you diversity less or equal than diversity of B. Okay, so kind of like it's a natural question to ask, like we want to maximize this minimum, we want to make this minimum as close as possible to the whole diversity. Okay? Okay, so one assumption that we have here is that we have enough individuals. That means that the minimum of these integers is at least k. Okay? So we have, at least we can put one single individual on each subgroup. And the second one, if you're familiar with the max mean fair division problem, this is analogous of that, but in the case of diversity. The thing is that in max mean fair division problem, the objective is a utility which is usually considered to be linear. But in this case, this function that we're considering diversity is highly nonlinear. It's the ratio of these two numbers. Okay. Okay, so any questions so far? No? Okay, so as I promised in our paper, we do a geometric approach. Let me give you some important properties of this function. One of them is that it's invariant under scaling. That means that the diversity of the value of lambda x is the same as the value of x. Okay, I just, sorry, here I'm putting the diversity, and you can clearly see that if you multiply x by lambda, then we get the same. Okay. So one natural intuition is that, let's imagine, for example, that we allow for fractional individuals. Then one natural option is that, okay, let's divide b by k, and then we get exactly the diversity, the same as diversity. But unfortunately, we cannot divide people in two. One natural option is to consider a balanced solution. Okay, let me give you an example for that. Is that, let's consider b to be 6, 15, and 21, and we have two parts. Okay, so one balanced solution would be, okay, I divide by 2 and then take the floor of this, okay, by component. And then x2, which will be the second part, is the remaining elements. Okay, so in this case, it would be 3, 7, and 10, 3, 8, and 11. But unfortunately, the diversity of the second group is strictly less than the diversity of the whole community. Okay, but the key thing here is that this is not the optimal solution. The optimal solution is actually x1 being 2, 5, and 7, and x2 being the rest. And the key idea here is that the maximum, sorry, the greatest common divisor of the vector b is 3. Okay, so I can divide every number by 3. So that will give us an idea of how to split the community in two subgroups. Okay, so these two vectors actually preserve the diversity of the whole community. Okay, and this will be the key idea for the first result of our work. Is it clear? Any questions?
So can you say it again, the difference between the two? So one is optimal, but the other one?
This one is also optimal, yes. The other one is not optimal.
But
because one of the diversity is extremely less than the diversity.
Okay, but they also, both of them, they preserve the diversity.
No, no, because the diversity of the second group in the top solution is extremely less than the. Okay. What you want is the second one, that all of them are equal.
Okay.
Okay. So in this case, by taking this balanced solution, you would not preserve the diversity. You will have to take this another approach.
Okay.
Okay, so when this is not the case, we go to a geometric approach, and that is the following. Let's imagine, for example, that we have a two-dimensional vector. Okay, so we can plot this vector b on a two-dimensional plane, and I'm plotting here from 0 to b. The segment in black would be let's say the community. Okay, in red I have the vector of ones, and actually one property is that the diversity of 1 is exactly R. Right? Because it's maximized when you have a uniform distribution. You remember this? So we'll give you the vector of 1 exactly 1, okay, R. Okay, and the second property is that the diversity is proportional to the square of the cosine of the angle between x and 1. Okay, why is this? Because it's just simply the representation between these two numbers. Okay. Okay, so what you want is, given this segment 0b, is to construct a piecewise linear function, okay, that I'm plotting with the blue, that kind of approaches to the segment 0b, okay? Because by minimizing the angle, I'm maximizing the diversity. Okay, so the diversity of this, for example, of this segment 0b is the angle with respect to the vector of 1. So in blue, if I approach more to the segment 0b, then I'm increasing the diversity of it. Okay? Okay, so the partition, just to clarify, of blue would be 0 to x1. This would be the first part. This would be the second part, and then the third part. Okay. Okay, so let me give you the first.
So that was a two-dimensional diversity.
Yeah, that was for the two types. But it's more complex form when you have higher dimensions. Okay, so the first question is, when can we guarantee that we preserve the diversity? So the main result here is that diversity is preserved if and only if the greatest common divisor of these numbers is at least the number of parts. Okay, and it will be clear in a moment. The key fact here is that the number of breakpoints of the segment 0b is equal to the greatest common divisor minus 1. Okay, let me give you an example for that. So let's say that we have b equals 5 and 7. Okay, if we plot this, then we notice that we don't have any breakpoint in the line. There's no integral point line on the line. Okay, so this GCD in this case is 1. So we cannot preserve diversity. Okay, there is no way to split this vector in two that we preserve the angle. But instead, if we have 4 and 6, then we actually have 1 in the middle. Okay, so in this case, the GCD is 2. We have 1 breakpoint, so we can produce 2 parts, which will be 0x1 and x1. Okay. Instead, or if we have 4 and 8, then the GCD will be 4. So we can divide up to 4 parts. Okay, and here I'm plotting a 3 partition. Okay, I'm plotting 0 to x1 and blah, blah, and then the final from x1 plus x2 to it. Okay, but you could have 4 parts. If you want to have 5 parts, then you will break this. Okay, because you don't have 4 breakpoints in the line. Okay. Let me give you an idea of the proof. So let's denote for D as the greatest common divisor. Let's do the implication to the left. Let's assume that the greatest common divisor is at least the number of parts. Okay, so we can consider the following. We divide B by D for the first k minus 1 parts, and I consider the rest for the last part. Okay, and it's clearly because of the property I'm putting there in the corner is that the diversity is preserved. Okay? And this is an integral number because it's the greatest common divisor. Okay, this is the easy implication. The harder implication is the opposite. So we are assuming that the diversity is preserved, and we want to show that the GCD is at least k. Okay. Sorry, the GCD is at least k. Okay. So let me k start the largest partition, the largest number of vectors I can have, in which way I can represent the diversity. So we know that k star is at least d. I can always, d is a feasible solution, so I can always output d vectors. Now we want to prove that k star is less than d. Sorry. Okay, so we take a partition that preserves the diversity. Okay, it's at least a diversity of xj is at least dv. So we can show that these vectors are aligned. It means that xj is actually proportional to the vector d. Okay, and finally we can show that these multipliers are at least 1 over d. Okay, so b is going to be the sum over xj because we have a partition. Then we can represent xj as alpha j times b, and finally lower bound by 1 over d, and we have k divided by d times b. So we can cancel, and we have k, sorry, here's k star. K star is less than d. Okay, so kind of clear, I mean, more or less the idea of the problem, the solution. Any questions? Okay, so let's go to the harder part. What is the best division that makes the least diverse group as diverse as possible? This is whenever we cannot guarantee what I showed you before. And the result before was for any number of types, okay? But in this case, we're gonna focus on 2 types, okay? Because it is easier to visualize, and 2 parts. Okay? So one naive algorithm, so as I said before, we want now, since we don't have a breakpoint in the segment 0b, we want an integral point above the line. Okay, there is always one point above the line. Okay, in which this point is as close as possible to the segment 0b. Okay, so we want this break for x1 to be as close as possible to the segment. One possible option of an algorithm is we check for all the possible solutions. This would be order b1 times b2. Okay. But this is unfortunately exponential in the size of the input because the input is a vector of numbers. This is exponential in that size, okay? Because of how we encode these numbers. The second algorithm is that since I gave you the idea of checking for the closest integral point, then we can actually iterate over the x-axis and evaluate and check for the closest point, right? This will run in order B1, which is still exponential in the size of it. Okay. So our main result is that we have an algorithm that actually finds the best division, find this point, x1, in order log square of the maximum between B1 and B2. Okay? And this would be in the size of the input because how we encode the numbers. Okay. And the key idea here is that these vertical distances, which is x, the distance that is x1 to kind of the same in the vector 0b, is in one-to-one correspondence. Oh, I have to hurry up. It's a one-to-one correspondence. Don't worry. Okay, one-to-one correspondence to these values: 1 over b1, 2 b1 minus 1 over b1. Okay, and you will see kind of the idea here. So let me give you a sketch proof for that. So just remember that the diversity of x is 2 times, because we have 2 types, the square of the cosine of the angle of x. Okay. So for any partition x of b minus x, we can assume that the vector x is above the line. Okay, because there is always kind of a symmetric way to see this. So in fact, the minimum between these 2 diversity would be dx. Okay, it's just simple to see the angle that this segment produces is much larger than the angle that this vector produces. Okay? The angle with respect to the 1. Okay, so by looking for the maximum, for the best, by looking for the best solution here, we're maximizing the minimum between the 2. We want the point x with the least angle. Okay, so for that we're going to solve the following equation. We have this equation of integrals in which Ti would be the remainder of this equation. Okay, and if you remember maybe in your arithmetic class, there is a unique remainder for this equation of integrals. Okay, so we can compute the distance. The vertical distance would be, okay, so I'm evaluating the x being I in the line of a slope B2 divided by B1. So I'm evaluating the point I in this line. Okay, and then I'm taking the ceiling of that, so it would be the closest integral. So the distance would be B1 minus the remainder divided by B1. Okay, and the remainder is in one-to-one correspondence since they are unique to these values. So this is one-to-one correspondence to these values, because if you move Pi in this set, you will get the other set. Okay, so in order to find the solution, we find the I stars such that this point has a vertical distance of 1 over B1. So this is the point that we want. Okay, and we can use this, do that by using the Euclidean algorithm that you may have learned in high school. And also finally, we have to prove that there is no other integral point between the line that kind of like the line that the blue line goes here and the black line 0b. Okay, we have to show that there is no other integral point between. But the main idea of proving that is that these are unique. Okay. Any question on that? I think we have like 5 minutes.
Yeah, 6.
I'm gonna. Okay, so the question is what happens for any number of parts, and this is much more complicated. But we show that we have an algorithm that we can find the best division in order k times the log square of, again, max between B1 and B2. And just to give you a brief idea of the algorithm is that we take the initial instance and we recursively construct smaller instances, okay? And we find a very small instance in which it's easier to find the partition. Okay? It's just solving an equation, okay? The key thing here is that these mappings into smaller instances are bijections. So you can map the points that you find in the smaller instance back to the initial instance, and then you solve it. That's the key idea. Okay, so just to finish the talk, so I talked to you a little bit about how studying the diversity when you divide the community in subgroups, and we use the Simpson index for that. We characterize the instances in which we can find the perfect kind of partition in terms of diversity. And we give a polynomial time algorithm for 2 types and any number of parts, okay? And the main tool here that we use in our work is that we use this geometric approach given this nice representation of the angle and also the 2-dimensional case. Okay, there are a couple of extensions. First of all, we don't know the computational complexity of this problem in general. It's not clear. And also, we don't have an efficient algorithm, even if it exists, for higher dimension, even for 3 types. And the thing is that in 3 types, you don't have a line anymore. You have a cone, okay? And this cone will represent the diversity of the community. And any integral point lying inside the cone would have better diversity than the community. And any integral point outside the cone would have worse diversity in the community, okay? And here in black, I have the vector of 1. So this cone is rotating around this vector of 1, okay? The other problem is that in 2 dimensions, we have 1 point above the line and we can have another vector below the line, okay? In here, you can have both parts outside the cone. It's even worse. So the thing is that there is no clear concept of vertical distance to the cone that could help us to find in a polynomial time the solution, okay? So there is no notion of a reminder anymore. And the other question is that, what if we use another type of indices? So there is a long-standing consensus on ecology, on the ecology community, that the Hill numbers are the ones that you should choose in order to measure diversity when you are trying to measure evenness or richness, because it has several desirable properties, such as the one I mentioned, but all more important for ecology. And these one are characterized by the following family that depends on parameter Q. It's this ratio. And if you set Q equals to 2, you will get the Simpson metric, okay? But for example, if you put Q equals infinity, then you will get the exponential of the interval. So you kind of like recover a whole spectrum of metrics with this family, okay? Again, of course, I mean, the Simpson metric gave us this representation with the angle, but you don't have this here anymore. So it would be 1 step complexity for the problem. Okay. Yeah, and with that, I would like to end the talk, and thank you very much.